Will you tell the live stream about drone? Yeah. So, is this a good level? Okay. So this is our first ever drone. It's designed with a full carbon fiber frame. It was made in-house. It is intended for the delivery task, which will be used in conjunction with the rover holding the arm. The goal of it is to find and locate items, communicate that to the rover, and then have the rover go pick up those items and bring them to the location specified. One of the other parts of competition is a astronaut task where an astronaut needs an item. In that case, the drone will go over to the astronaut much faster than the rover can, read the sign, figure out what item is needed, then locate the item and tell the rover where to go by dropping a waypoint on GPS. That will be seen on base station, and the rover will navigate over there. The entire drone is under 5 kilograms. Its final weight will be about 4.3 kilograms. The propellers are 26-inch propellers. It's a fairly large size. The reason for that is because our competition simulates a Mars environment, which has a thinner atmosphere. The way we simulate that is by adding a dummy load equivalent to the battery's weight. With a drone with smaller propellers, that dummy load massively decreases the flight time. With larger ones, more thrust is generated. It's more resilient to that dummy load, and we can have a longer flight time because of that. The end flight time will be about 25 minutes. Yeah. You guys would like to put the microphone to your tank.
Okay, this is the microscope, and it's the first sort of test we perform on the soil before we do anything else. It's useful because it helps us get a better look at grain size in the soil. So this is a good example of a good soil because there's big pieces and little pieces, and that means it's going to retain water very well. So if we look at a soil sample and it's just sand, that's not going to retain water very well, and we're not going to waste our time on that.
So the Raman spectrometer is another thing we're going to be using for soil identification. And how it works is it's based off of the Raman effect, and the Raman effect happens when a molecule is excited, and sometimes when that molecule is excited, a different color wavelength bounces back. So those are the different based on the different wavelengths, we're able to tell what it's made out of. So here the flashlight is standing in as our soil sample. So if I turn this on,
so you're all going to use the same.
it'll go through our probe here, and the white light turns yellow because we have a filter in there, and that filter blocks out any automatically reflected light, and also the laser light, which could overload our sensor. It bounces off of this mirror onto a diffraction grating. The diffraction grating turns just that like blob of light into a colored spectra that we can then read. This just bounces it onto the sensor, and if I put this in front of the sensor, we can actually see that spectra from that white light. It's pretty cool.
These are all the boards that go inside the rover. Here we have the battery management system. So basically it monitors the things like temperature, the current, the pack voltage, and the overall voltage in the battery. And if it gets above or below a certain level, then it will cause the rover to e-stop. This is the power board, which manages the power delivery to the rest of these boards here. Let me see here. Over here, we have arm board. That controls the individual servos that are actually on the arm. These also are connected to limit switches on the arm, so it knows about the orientation of where the arm is, and it'll do things depending on that. Here we have a MOCO breakout board. So those control the individual servo motors on the rover. And let's see, wait. Which one is this one? Oh, this is core board. Okay, so these control other motors on the board, such as the drivetrain. So this allows the rover's wheels to move and controls the speed of them. And here, last one, we have the differential GPS breakout, which allows the GPS to talk to the rest of the rover. So yeah, here's all of the boards that go inside the rover.
All right, so we are the software subteam. We're currently in the process of rewriting our entire Python codebase in C++. Currently, we're working on integrating our new code with the simulator. So you can see the rover here right now is just going in circles, just doing its thing. But this is how we can rapidly iterate on our code and test it virtually before we actually go out and physically test the rover. So in competition, there's 4 different tasks, one of them being the autonomy task, where the rover has to drive itself completely using computer vision and GPS. So using the simulator, we can simulate that, and we have these AR tags in the sim that we can detect using virtual cameras. So we can basically emulate everything that we do in competition virtually on the computer here, which allows us to make really quick progress with our software.
So this is our base station. This is a front end application that we use to control the rover remotely. So the rover works via a distributed network architecture that we send packets to over our signal stack up here in order to do things like drive the rover, check the battery voltage, control the auxiliary systems like the arms and the science system, as well as view camera feeds. So this is a very robust system with a lot of functionality, and there isn't any other good way in order to control the rover.
Okay, this is our arm, our first Cartesian arm in the history of the Mars rover design team. This arm, we have 3 linear directions. You have your X right here. You have your Y, and then you have your Z. And this allows it to be very simple for the operator to control the system. It allows you to think very smoothly as you operate a mission, such as typing on a keyboard. It's very simple to say, oh, I need to go up, and then I need to go left. And it makes it really nice for the operator. We have a dual end effector system so that for every task, we have one gripper that's able to grab onto tools and rocks, and then another that's able to type onto a keyboard, tighten bolts, operate joysticks. We have a wrist that allows us to adjust the pitch of our gripper, and individual rotations of the grippers that allows us to really operate things such as plugging in a USB, where we have to have a very precise positioning. I hope you enjoy our new gripper.
Fix the wheels to use indoors, and as opposed to these ones, which are kind of scratchy and very hard to use on a hard surface, you've got these malleable wheels, which are really squishy because they're made out of TPU filament. So mainly because of the filament, and also because of this honeycomb pattern, which has like an open middle, which allows it to flex a lot more. So we're trying to use these indoors. They do take a long time to print, though. It's like 4 days to print, but they turn out nice. Yeah, so we actually have this one kind of in contrast to our actual wheels, which are made out of carbon fiber. We make them out of this shape out of carbon fiber because they're trying to get over hard, rocky terrain. So we actually kind of need more of a grip and more of a like rough surface on the wheels. So we actually make all these in-house. We do all the carbon fiber layups. Kind of here's an example of the material of it. And you can see another wheel down there of one that we've actually made in the past. All of these parts on the table are manufactured in-house by our team. We actually do a lot of the machining here with the students doing training for mill, CNC mill, lathe, CNC lathe, etc. And it helps to it helps the students learn to design well if they know how to manufacture. So that's a good bonus of it.
So this is our science actuation system. This enables all of our scientific experiments on site, where we sensor samples for different signatures that indicate presence or absence of life. Yeah. So on the far end is our auger gantry. So that will plunge our auger to below 10 centimeters in the ground. That way we can test relative humidity and temperature and collect soil samples of significance in a biological context. And then the near side gantry will receive all of our instrumentation, consisting of an Fourier transform iris spectrometer, a Raman spectrometer, a reflectance spectrometer, and a microscope for microscopic imaging. And all of those will tell us a little bit about the composition of the soil and what biological indicators we have that indicate whether there was life present at one point or whether there is currently life present.
Let me know. We're good. So this is our base station. This is our interface between us and the rover, how we kind of control it during competition, how we get the data from our cameras to see where we're going, and how we understand everything's going well and according to plan. On the left here, we have our rover overview of network, which shows us data on what's going on with the boards inside the rover, making sure we have a stable connection to them with our signal stacks. Green means good, red means not good, and white means we're not connected. And if you see any white on there, it's because it's being shown up at different places at the design center today. Next, we got our red application. This is our kind of overview of everything that's going on the rover. We got a map on the top right, shows some GPS data on the top left, and below that, we've got some power and BMS data. That's pretty important because we just want to make sure the battery's doing all right, and we just want to make sure that's a good thing because battery is not doing all right is not a good thing. Next, we've got RAM, which is our rover attachment manager. This is where a lot of our tasks are focused on. So we got 3 slides. We got ARM, science, and autonomy. ARM just shows us some basic controls for that, enables us to control the arm, and gets us some cameras that are put on the arm. Science system is a little bit different. We get some data from the science systems on top of that, whether it's different Raman spectrometer, and humidity, or temperature. And then we go on to autonomy. Base station does not host autonomy. That's hosted on a Jetson on top of the rover. But base station does start autonomy, and it enables us to add marker legs, add gate legs,
clear waypoints. And we also have a state diagram which shows us what state autonomy is currently at. Following that is RID. Right now you don't see a lot on there, but that is the point. It is a rover imagery display. It lets us really control what we want to see on that fourth screen. That's fully customizable with what we want to do, and we can add any implementation of any different science or system on base station over there. So if there's a task that we require another view for, we can easily put it on there. This year, we decided to make base station more modular. We started with a goal of 3 cases, but we split it down to 2. We got one big case with 2 distinct interfaces, sorry. 2 monitors each, and each of these have a keyboard and mouse control to them. To the left, we also have a small base station case. This case could be used for testing. A lot easier than taking this big case out to testing. It's a lot heavier, or a lot lighter than the bigger case. But that also has the same features, controller, mouse, keyboard. And this just allows us to be more modular. If more people are in a U-Haul controlling certain parts of the rover during a task, it's going to be a lot easier if they have more keyboards and mice to control it, rather than fighting over that one instance. So that's our base station.
Hello, testing. 1, 2, 3. Hello, can everyone hear me? Is that as loud as it goes? Testing. 2, 3. Testing the microphone. Testing. 1, 2, 3. Is that good? All right. Is everyone able to hear me? So I can barely hear myself. Turn it up. And hello. Testing. 1, 2, 3. Testing. You good? All right. Hello, everyone. I want to go ahead and welcome you all to the Mars Rover Design Team's 2024 Rover Reveal. I'm excited to have you all. I hope you all have had a chance to walk around and look at all of the cool projects that we have on display for you all right now. My name is Liliana. I am a senior in aerospace engineering, and I am currently the CEO of the Mars Rover Design Team. I joined this team my freshman year, so I've been on the team for 4 years. My freshman year, I actually joined a lot of different clubs and organizations. Really wanted to get involved. And the one that obviously has stuck with me throughout all my time here has been the Mars Rover Design Team. And I hope you all can get a glimpse into why that is throughout this event here today. So yeah, all of our members have been working super hard leading up to this point. And I know they're all super excited to finally be able to reveal all of the hard work that we've been doing for the past 8 months. They should all be super proud of all the work that they have done leading up to this point. So yeah, today as we go ahead and reveal our 2024 Mars Rover, I hope you guys can all, I thank you guys all for coming today to celebrate all of the hard work that they've done, all the effort they put into this team, and everything that has happened leading up to this point. But before we do that, I want to go ahead and talk a little bit about what our team does and what goals our team kind of works towards. If you guys could position your attention to the slides that we have up here. We'll have some pictures up there. I don't know if leads over here want to kind of like duck out of the way. But yeah, our team, at the end of May each year, our team loads up in the S-Stoke vans and we go and we travel out into the middle of the desert in the middle of nowhere in Utah. We compete in a competition called the University Rover Challenge. And at that competition, we are challenged to be able to design, build, and compete the next generation Mars rovers that help aid astronauts in various different tasks on Mars. And what's super cool about our competition is that it's an international competition. So we compete against teams from all over the world, from Australia, Canada, India, Poland, all over the globe. They all come and meet in Utah to compete their rovers. And something to note is that sometimes a lot of these teams are made up of, for instance, all senior engineers and scientists who are working towards their rover for their senior design project. And sometimes we're competing against teams that are made up entirely of graduate students who are working on their rover for their graduate research projects. And what's cool about our team is we're made up of almost entirely all undergraduate students. And our work that we do on this team is very freshman driven, and the freshmen are the ones, and new members are the ones that are designing the projects on our rover that you will see today. So yeah, other than that, we will kind of jump into what our team all kind of does at our actual competition. If you want to go to the next slide, Eli. So at our competition, we compete in 4 main tasks. Two of our tasks have the robotic arm on our rover, where we have to be able to control the robotic arm and the rover through onboard cameras at our base station that we have back against that wall, if you guys took a look at that. We have to be able to pick up different tools, locate different tools, locate different objects in the field, pick them up, carry them across different types of terrain, and deliver them to all of the astronauts out in the field for that mission. We also have our equipment servicing mission, where we have to be able to use different tools and do a lot of fine manipulation type tasks, typing on a keyboard, flipping switches, pressing buttons, all sorts of stuff. What's cool is that our auxiliary systems are modular. So we can take off the robotic arm from our rover and put on our science system for the science mission, where we have to be able to analyze different soil sites out in the field and be able to use all of our onboard instrumentation to determine if there is a presence of life in that soil or not, as well as collecting a soil sample and caching it all on board the rover to later give to the judges at the end of our mission. And finally, we have our autonomy mission, which is completely hands-off, so we're not allowed to be able to control the rover for that. The rover has to be able to navigate the course all on its own without our help. So as you can see, there's a lot that goes into our rover, and because of that, we have a lot of different disciplines and majors that join our team, and a lot of different sub-teams. So I'm going to go ahead and hand it off to some of our sub-team leads so they can go ahead and introduce each of our sub-teams and what all they work on throughout the year.
Is this on? I think it is. Oh, it is. Okay. Hi, everyone. My name is Abby. I'm a junior in mechanical engineering, and I am one of our mechanical architects on the team this year. I'm going to give you a brief overview of our mechanical subteam and what the purpose of it is and how the subteam's made up, what we do. So starting, our subteam's broken up into 4 sub-subteams, one might say, and that is drivetrain and chassis, manipulators, science actuation, and composites and tooling. So 3 of those represent the 3 main mechanical systems in the rover, and then one of those is slightly different and kind of has hands in all of them, and so I'll talk about that one a little bit first. That's a new sub-team to this team, and that's composites and tooling. So that team, we realized, was an absolute necessity when our team started branching. People took more of an interest in, and then our team started using more of the composite materials and the composite manufacturing methods as opposed to our traditional additive and subtractive manufacturing. And so that has a hand in all 3 of our mechanical systems and plays a big role, as well as that tooling role. That is all of our ground support projects, everything that is essential to our team and our performance and competition, our experience at the SDELC, but is not technically on Rover. So that's what that sub-team takes care of. They've done a lot of great work this year, very dedicated members, and have been a huge help, absolutely vital. They enable the success of our other 3 sub-teams. So to go down the list, I know you guys just heard about that breakdown of our 4 tasks of competition, so I'll kind of relate the different sub-teams and systems as to how they play into those. So first, our drivetrain and chassis. That's our suspension and our frame and all that attaches to our frame. So that's present during all of the 4 tasks. That has to be stable and be able to traverse a wide variety of terrain as it supports all 3 of our systems that can go on the front. Like Liliana said, they're modular, so we swap those out, but the drivetrain stays and has to be able to remain balanced and steady as it traverses terrain. And it also has to interface. It's our largest mechanical interface with electronic components. All of the electronics go inside that frame, at least a lot of them do. Some are housed in the other components, but that's where most of them are, our battery. And we have to have interfaces with our signals and our cameras, and that's all attached to that frame. So that's a large interdisciplinary effort is to figuring out how our frame is going to work. But that's our drivetrain and chassis and what that sub-team works on. Next up is manipulators. So that's our robotic arm. Typically, you guys saw over there on our cart driving around. So that is what helps in our equipment servicing and our delivery missions. So this year we have those 4 linear axes and those 2 rotational axes that are to make those, that's capable of making those fine movements to do things on that lander like flip switches, type on a keyboard, but it's also capable of lifting a lot of weight, have a lot of torque so that it can carry objects across terrain and remain sturdy and connected to the frame and carry those objects to astronauts in the delivery task. Then that's a bit about what the manipulator sub-team does. Lastly is our science actuation team. So that is going to be, they support our science analysis equipment. That's going to be talked more about in a couple slides on our science slide, but that system houses, it also has linear movements. It houses all of the instruments that are used to collect environmental data, and we have to make sure that those instruments are in a good position, and we have an auger on there that has to be able to dig into the ground and collect a soil sample and cache it for later. All of those movements go into making sure that our instruments collect reliable data that we can show and explain to the judges after our science task. So that's a little bit about how our sub-team is broken up. Essentially what we do as a mechanical sub-team is we're all trying to follow the complete engineering design cycle. So that be the conceptualization of the design itself, analysis and verification, then we have manufacturing, then assembly and integration, testing, and then iteration. All of those big fancy engineering words basically means that we design the systems, then we make them, we put them together, we see how they work, and we continuously try to make them better, all the way up until we leave for competition. We're trying to improve upon our systems, find their weak points, make sure we're meeting all our competition requirements that we set, that URC sets forth and that we set for ourselves internally, and yeah, making sure we're continuously iterating and trying to put the best product out there. We do not ever say like our rover's finished. We definitely don't take our finished rover to URC as we say. We take our most up-to-date revision because we're constantly changing it and trying to make it as best we can. Lastly, the biggest thing I want to get across is that we are here. It's the reason that all the leads joined the team initially, kind of like Liliana said. The reason that we're still here on leadership is because we have gained so much applicable technical experience from this team and technical skills, and we just want to pay forward what the opportunities that we've given on this team to give the opportunity to your students as well. And it's been all of our pleasure to work with your very hardworking and dedicated students. It has been a lot of fun, and we're excited to see the team continue to grow in the next few months. But mechanically, we have had a lot of really dedicated and interested people, and it's been a joy to a lot of what we do is leadership. It's just as much technical work as it is training. So we've enjoyed having students that are willing to learn and wanting to learn along with us, and that are very ambitious. So it's been a fun year for mechanicals. I know we have a lot to do, but yeah, that is an overview of what we do here in the mechanical sub-team.
All right, my name is Alex Wortman. I'm the electrical architect. I'm the head of the electrical subteam. On our subteam, we create electronics that power all of the mechanical systems and interface with all of the science and software systems. So to do that, we have to make a lot of custom electronics, which means we have to go through the whole design process of electrical engineering, computer engineering, making PCBs, as well as working on embedded code for all of those PCBs. We interface with a lot of motors and servos, as well as gain data from a lot of different various sensors. So there's a lot of interfaces going on our team, as well as we take all of our new members through this process.
And implement software in a way that allows us to efficiently control our systems, and that splits us into two distinct sub-teams. The first one is the autonomy sub-team, which relates to our autonomous navigation task, which uses GPS navigation algorithms and computer vision in order to find a goal marker and basically drive up to it. And then the other sub-team that that our team has is the base station sub-team, which is our massive control interface. It's a big computer that we drag out to the desert every year, and it uses our control software in order to view battery information from the rover, send drive packets to the rover, view our camera feeds, etc., etc. So our goal, our prerogative with our software is to design it in a way that makes it as efficient and easy to use for everybody as possible. And in order to do that, we, implement a lot of testing and a lot of thorough vetting, code reviews, that sort of thing, in order to make it work properly. And then let's say somebody joins our team. So we train our members in the fundamentals of all of the software, all the coding skills that they need to know, not only to help them succeed on Rover, but as well, it gives them a lot of skills to work in a general professional environment. It ends up working great for their careers. It ended up helping a lot for me as well. So to all my members, I want to thank you all for being active in our team, and thanks to you, we're going to do so well in competition this year.
Hello, my name is Aster. I am the science analysis team lead. I work very closely with Ryan and Drew. Ryan, Drew, and Brady, I don't know where he is. But Ryan is the science actuation lead, and Drew and Brady work on the electronics for the science system. Like it was mentioned earlier, in the science task, the rover has the science system mounted onto it. We're just kind of put into a circle about a kilometer in diameter, and we have to use clues of the geology to determine sites that could be habitable, something like a creek bed, some interesting rocks. We then take the rover over there and use all of our onboard instruments that the students make to analyze the site for absence or presence of life. And if we find something interesting, we then take a soil sample with our onboard auger and cache it to give to the judges. And the science analysis people back in the control center will give a presentation on what they found to NASA scientist judges. So pretty intense. All of the instruments are sold retail for about $10,000 to $25,000, and on the team we make them for a total of $3,000. So there is a lot of work being done by all of your kids to create and deliver on all of these very, very complicated instruments. Aside from teaching, a lot of things that Ryan, Drew, myself, and Brady all try to do is give opportunities. I was given a fantastic opportunity last year on the team. We developed a first of its kind system, took it to Utah, got a university paid trip to a different state. And there was a paper written on it, which are all things that we are trying to get to do for your kids. So thank you very much to all of my members, and I hope to see you all over at the science table.
My name's Jesse. I'm the drone sub-team lead. I've had the privilege this year to lead a small team of very dedicated individuals in developing a system that we have never had on Mars Rover before. The purpose of this system is to aid in the delivery task, which is working in conjunction with ARM to find items and deliver them to the places that they need to be. To accomplish that, we have various sensors on the drone to detect those items and then quickly and reliably transmit the location of those items back to base station, where they can navigate the rover over to that place, pick them up, and put them where they need to go. If that sounded like a lot of different things, that's because it is. We're a very cross-disciplinary team that needs to integrate with a lot of different sections. Because of that, my members have had to wear a lot of hats. They've been very versatile in pursuing a lot of different disciplines and adapting to whatever I need them to do on a day-to-day basis. They work with software for the component of the drone that integrates with base station. They work on composites to design the frame. They wire things electrically to make all of it come together. In general, they've just been all around amazing. And for that, thank you very much.
All right, and then finally we have our PR sub-team, which is pretty much just made up of all of the members who are already part of different sub-teams, and they come and they help us out with all of the different events we coordinate, both local community events, showing off the rover at STEM events at the local middle schools and elementary schools, as well as a lot of different on-campus events. We've gotten to have the rover flip the coin at the homecoming game, which is pretty cool. We get to hand out candy at Boopalooza downtown in Rolla using our robotic arm to all the kids on Halloween. So we do a lot of various events, both on and off campus throughout the entire year, and a lot of people that are on different sub-teams come and help out with that. We also take care of documenting the team's year through all of our photos and videos that we take, posting those on social media throughout the year, and then finally assisting with the competition documentation that we have to turn in order to get into competition and stay in competition and get good scores throughout the entire year and getting into the University Rover Challenge. So that is an overview of all of our sub-teams. I'm going to hand it off to Grant because he wants to talk a little bit about technical stuff.
Yes, I know. Hello, there we go. That's kind of working, I think. Oh, I'm Grant Bergstrom. I'm this team's Chief Technical Officer, so I'm in charge of all these lovely people back here across all those different sub-teams, which it's quite a bit to think about. So Mars Rover, as you've seen, has a really wide scope of things we do, from mechanical with all our composites, software, rewriting the entirety of autonomy in C++, electrically, working to develop all those PCBs and iterate on those and streamline those, make those smaller, more effective year after year. Part of the reason Rover competes in URC is because that competition is so wide, because it creates so many opportunities for engineering students from all disciplines, from physics, biology, comp sci, comp EE, mechie, aero, engineering management, even to do great work, to do world-class work on a incredibly complicated machine and target this really high goal. In the process of that, there's a lot of really interesting problems to solve, really good problems to solve, experiences to give people in project management and leadership and just technical skill and streamlining their own engineering design processes to become world-class engineers. So Rover intentionally has the breadth of stuff we do as a team, and we've got a ton of really cool stuff this year, from rewriting like the entirety of autonomy in C++, and drastically speeding that up from the instruments on science, which I don't know if anyone's checking out the interferometer back there, but we're working on that as a R&D project, and that's insanely sensitive. You can push on the metal plate and see that interference pattern change, and that's not a lot of deflection. That's not millimeters or anything. That's like nanometer scale. We've got the boards and working on current sensing this year and streamlining the battery and like reducing the weight of that by 1 kilogram, 2 kilograms down to what we actually need for a task. Designing that in a way where it can switch batteries between tasks to get the same operational life out of the rover at a lower weight. So that's a ton of really cool stuff this year. I'm very excited for where we can get to with at the end of the year before competition, with getting systems that work effectively and reliably, that we can take out to URC and win this incredibly large, incredibly complicated, challenging engineering competition through the dedicated work of the, we got 17 leads, 4 members of e-board, and then the new members that go along with that, the 50, 100 new members who everyone's work is essential for going out and doing that and winning URC. So. Yeah, it's been a ton of really good work put into this rover so far. Got a lot more to go. Yep.
All right, testing. Hello, is it working? Yes, okay. Cool. So yeah, as I said in the beginning of today, I have been on the team for 4 years. I joined when I was a freshman, and the Mars Rover Design Team is not the only organization that I joined when I first came here as a freshman. I was super ambitious and wanted to get involved in something that would have more to offer me than just the traditional college experience. So I took opportunities I took pretty much any opportunity and every opportunity that was presented to me. But obviously, as you can all see today, the Mars Rover Design Team is the one that stuck with me, and the one that I remained dedicated to throughout the past 4 years of my college career. And I definitely do think that there's a reason for that. What drew me into the team was how the team set standards of excellence for themselves, but I think what kind of kept me around was the values that this team keeps throughout every single decision that they make throughout the entire year. The Mars Rover Design Team takes a lot of pride in being a student-led and operated organization. We take a lot of pride in being completely student-led, and when we say that, we really do mean it. It is our members that are driving the decisions that we make on our team on a daily basis. It is our members that are training each other, are leading each other, and that are choosing how to move forward and how to take the next steps on our team. And I think that's pretty cool because no one else is telling us what to do or what decisions to make or how to move forward in future years. But our members take it upon themselves to be able to make those decisions and are always trying to push our team to be better and push our team to top the accomplishments that we've made in past years. Our team also takes an immense amount of pride in being a student-led organization, as well as having a hands-on work ethic throughout the entire year. So some examples of that, we take immense pride in being able to machine all of our aluminum components that you see on the rover right here in the design center and compete with those parts on our rover at competition. Whereas some of the other teams that we compete against, they will just outsource their machining operations to professional machine shops in the areas and use those types of components on the rover. Another example is we take a lot of pride in being able to manufacture all of our own carbon fiber tubes and linkages that you see on our rover suspension. And I think that's pretty cool because a lot of the teams that we compete against at URC are just buying professionally made components and professionally made tubes online on the internet and using those components on our rover. So we take a lot of pride in being able to do things ourselves, and we don't do that because it is the easy way to do things. We don't do that because it is the most efficient way to do things. We don't do that because it is the smartest way to do things, to get a rover together and be ready for URC. But we do it because at the end of the year, we can look back and say that we made that rover. And when we say that, we really do mean that we made that rover down to pretty much every component that you can see on it, which I think is really cool. And something that is probably the most important to me and that has stuck out with me throughout my years on the team has been that the Mars Rover design team takes an immense amount of pride in the passion that they have for the University Rover Challenge, for our rover, and for our team in general. There's not another student organization on campus that I've seen have a level of dedication to their organization as ours does. I'm not even going to get into the amount of hours that I know some of our members spend in this building and working on Rover throughout the weeks, because I know that a lot of your parents are in the crowd right now and they probably don't want to know what that number is, so I'm not going to tell them. But believe me when I say that I know the members of this team are super dedicated to the team, and I've never been a part or seen a part of any other organization where the members care so much about that organization, care so much about the work that they are doing in that organization, and care so much about each other and are always there for each other and building a family out of this team. So as I'm here today about to reveal our 2024 Mars Rover, I'm reminded of all of the reasons why the Mars Rover design team has been a part of the my last 4 years here at college, and all of the values that make up our team and make me stick around and want to pay that forward to all of the new members that we have join our team year after year. So with that being said, I want to go ahead and reveal something that I know everyone on our team is immensely proud of and takes a lot of pride in right now. So on behalf of the Mars Rover design team, thank you. On behalf of the Mars Rover design team, I want to go ahead and present our 12th ever rover. Yeah, go ahead. Hyperion. A ton of hard work has gone into this rover, done by all of your students here today, and you all should be immensely proud of them. They should all be immensely proud of themselves, because it takes a really strong team to get to this point, at this point in the year, and you all should be super proud of that and all you have accomplished so far this year. That being said, every year to get into competition, before we're actually invited to the Mars Desert Research Station to compete in the University Rover Challenge, we have to submit what's called a systems acceptance review video, where we have to demonstrate that this rover here is capable of completing all of the tasks that are given to us at competition, and that we are able to help aid those astronauts on Mars before we actually go and demonstrate that. So I think on the next slide, Eli's getting it set up, but we will go ahead and show you all our SAR video that we just submitted last week for competition. We should hear back about our score and regarding our acceptance into the competition in the next couple of weeks. A lot of hard work went into leading up to this video. So once Eli gets that pulled up, we'll go ahead and demonstrate all of that. The Mars Rover design team at Missouri S&T has been hard at work since URC 2023. Made up of scientists, engineers, and business specialists, our team has been focused on designing, analyzing, and testing systems capable of completing URC missions. The Mars Rover design team is proud to present our 12th rover, Hyperion.
Our base station has been expanded and divided into 3 distinct modules by migrating our previous GUI application to a robust web server architecture. Leveraging Vite as our hosting solution, the server integrates all features previously employed by our Red application for control of Hyperion. This modular base station can be adapted for each different mission and mitigates delays from relying on a single control interface. Our signals overhaul aims for higher data rates, increased range, and better reliability. A managed network switch optimizes data flow through 900 MHz and 5.8 GHz spans, while the rotating signal stack improves signal transmission and reception. This boosts available bandwidth for 8 simultaneous camera streams over a UDP-based video streamer, available from any device on Hyperion's network for near real-time video in our control application.
Hyperion's new iteration of our custom Mantis suspension features optimized composite structures, telescoping signal masts, and simplified mounting systems. Our team uses in-house manufacturing techniques to fabricate our lightweight yet robust rover, capable of navigating tight paths, scaling steep inclines, and withstanding vertical drops. Powered by a custom 6S 8P battery, Hyperion's distributed electrical architecture includes individual cell voltage, current, and temperature sensing. The power distribution system offers current sensing for each power connection on the rover. Camera gimbals offer extensive viewing coverage of Hyperion and the surrounding environment during operation. Paired with our new Cartesian robotic arm, the rover can locate, carry, and deliver objects across various terrains. Accompanying Hyperion will be our team's first ever drone, featuring a custom-made X-frame, cube orange flight controller, and 30 minutes of flight time. The drone is currently being developed for teleoperation and autonomous capabilities to help aid our rover in the successful completion of the delivery mission.
Hyperion's new Cartesian robotic arm is comprised of 4 linear and 2 rotational axes, providing the control, strength, and range of motion necessary for fine manipulation. Each axis features a brushed DC motor energized using the H-bridge method implemented on custom breakout PCBs, allowing for easy maintenance during testing. The arm utilizes both absolute and quadrature encoder feedback for reliable closed-loop and 5-dimensional inverse kinematic control. Limit switches at the end stops of each linear axis serve for startup calibration and as protective measures in case of encoder failure. Our dual end effector design includes an under-actuated gripper for lifting and transporting heavy objects, alongside a multifunctional utility end effector for precise operations. Cameras mounted at the back of the rover and arm's end facilitate closer visual inspection and easier object alignment, enabling Hyperion to perform the dexterous tasks necessary for equipment servicing mission.
This year, our codebase has been rewritten in C++ and is designed for peak performance and modularity through the use of a multi-threaded active object design, enabling important features to maintain a high refresh rate regardless of data demand from other threads. The rover's differential GPS enables precise point-to-point navigation. A Z2i stereo camera, 2 Z minis, and a fisheye camera are used to detect surrounding objects and air tags. For navigation, an A-star pathfinder is used to chart the shortest path around obstacles to a goal waypoint. Then, a lateral Stanley controller guides the rover along this path, and differential drive inverse kinematics command the rover's drivetrain in an intuitive manner. After arriving at a waypoint, the rover will enter a customizable search pattern to scan the surrounding area. Cameras will continuously search for AR tags and objects using OpenCV's Aruco library, and a set of custom-trained YOLO models. Finally, an LED matrix signals the autonomous state of the rover, enabling Hyperion to complete the autonomous navigation task.
For the science mission, Hyperion utilizes a new science system with 2 single-axis Cartesian gantries. Onboard cameras document wide-angle and high-resolution pictures for the investigation of multiple sites, while locations and elevations are retrieved from our rover's differential GPS.
The system is equipped with a microscope for soil analysis and spectroscopic instruments designed for life detection, including a custom-built Raman spectrometer and a reflectance spectrometer. These instruments enable the identification of mineral samples, amino and nucleic acids, complex organic and biological structures, and organic solvents within a sample.
For a site of particular interest, an onboard auger extracts a soil sample up to 15 centimeters below the surface. The sample is then securely cached in a container, distinguishing soil depth for later evaluation.
Leading up to URC, our team is not only refining Hyperion through rigorous testing, but also maintaining a focus on R&D projects, including structural composites, a custom FTIR spectrometer, and more, driving innovation and pushing the boundaries of our systems. We thank you for your consideration to compete this summer. Scientists, but we also testing, we good? But we also have to be able to produce a nice, good quality video to submit to our competition. So on top of all of the technical work that they're doing, we also have a lot of different styles of work that we have to do in order to get that video together. So everyone on the team should be super proud of everything that went into that and getting up to that point. So next up, we wanted to kind of open up the floor to all of you guys and give you guys an opportunity to ask any questions you guys might have about our team or about our rover to any of our leads that we have up here. So do we have anyone that has any questions regarding anything? Yeah, go ahead.
So our competition is designed to only simulate the atmosphere of Mars by adding a dummy load on equal to the battery weight. We don't consider the change in gravity specifically. It's kind of integrated into that requirement of competition. So that requirement severely reduces the flight time of a drone that would be used in our atmosphere and changes the design goal by a lot.
Anyone else have any questions? Yeah, go ahead. You guys can just shout it out if you guys have questions. Go ahead.
And so for the autonomous mission, does it have to constantly attach the appropriate stuff? You're not allowed to attach it, or you're allowed to set it up to the autonomous mission because whenever, if it was Mars, no one would be allowed to set it up.
Sure. Thankfully, kind of like Jesse just said, it is a Mars simulated environment. So we do have, this would be in the case that we do have astronauts there with it on Mars, because we do indeed, this is our autonomy head on the front right now, but we do have that on before we start the autonomous task. So before each task, there's 10 minutes of setup time that requires us to get the rover in the state that we want it to be in before it has to start. So we have 10 minutes, we get that thing on there, and then it's hands off after that, so then it does its thing. But yes, this would be in an environment in which we already have astronauts that can do that for itself. But yes, so yeah, we do have that on there. It does not have to attach that itself. It's a separate system. Yes.
That's a good question. So every year, our team kind of goes through. Oh, he asked. Sorry, I want to repeat the question for the live stream. He asked why we chose the name Hyperion. And each year, our team kind of goes through a voting process. Our team historically has stuck to like Greek and mythological. I can't say the word. Greek mythology type names and gods and things like that. That usually represents things related to Mars or space or planets or stars and things like that. So all of the members of our team are able to submit any name they want, and then we go through an entire voting process and let the members of our team actually decide what our name is going to be for the server. I know it's related to like stars and stuff. Do you know the actual like word for word meaning?
Is this working? Okay. So Hyperion is the Titan, father of the sun, moon, and stars. So I believe the name suggestion for one of our members is because of how our rover is doing many new things that we've never done before, like the drone, our spectrometers, things like that. So we ended up voting and deciding on the name Hyperion to fully reflect our rover and our members on it.
Yeah, go ahead.
What were some go back design or
Who wants to answer that one?
I'll go ahead and answer. So there's a running joke that science has an obligatory redesign in the middle of the year every year. We kind of always have one of those oh crap moments. This year we went into the year with the intent to keep chemical assays on the system, and then about halfway through the year we decided that it wasn't. After designing most of our entire system, we decided it wasn't worth the investment, especially with how little we were getting out of it. And decided to invest that weight budget and that cost budget elsewhere into the spectroscopic analysis. So we had that whole mid-year redesign. A lot of late nights that week. Yeah. Sure.
One more from science. If you guys have been over to the science table and you've seen the interferometer, like Grant mentioned, it is sensitive, but I don't think there's a really good way to demonstrate how sensitive. As you saw when the rover drove out, it moves quite a lot. And the way that an interferometer works is it works based off of the laser's interaction with itself. So that plate that it's on can detect deformations up to the wavelength of the laser, which is 532 nanometers. So if I had it set up on this part of the floor and somebody over there was clicking a mouse, the interferometer can detect it. And realizing that is how sensitive that thing was and that we want to put it on the rover was a bit of a moment like that.
To add my little 2 cents to this. So for context, the drone was a part of competition last year, although we never manufactured one. In that task last year, it was for the autonomy task. So before rules were released for this year, we were operating on the idea that it would still be used in the autonomy task. A lot of design happens over the summer and towards the beginning of the year before those rules are released. And the entire thing was designed for the autonomy task. But then rules came out, and it was realized that it would be used for the delivery task. So all of the math and high-level design that had been done over the summer for the autonomy task had to be redone in about a week and a half for the delivery task. That was a couple long nights.
All right. Well, if we're all giving stories, we know we all have them. To give, I mean, just a recent one. I know we built, so something cool that is specific to this team this year is that this is my third year on the team. This is the first year where we have had on our system, in our system acceptance review video, you probably wouldn't be able to tell, but we can tell that we've had all completely new mechanical systems. We have not, partly because we switched around the ways that we mount our systems to the frame, but we didn't have the option to revert back to last year's ARM, last year's science system. We didn't have the option to use a different suspension, things like that, all of which I've seen in the past because we haven't had time. So this team has been able to come together and make all new systems. That being said, we were in crunch time for a couple weeks and we're working very, very hard. So our ARM, I know specifically, we got the footage that we needed for system acceptance review, which was about, I guess, a week ago today. But just about like the day after, like 2 or 3 of the axes stopped working. So we had a meeting on Monday as mechanical leads and with our members, and we're like, okay, so what are we going to do for it to be working for reveal? So we, throughout the nights this week, we're making a couple different changes. We still have a lot more to make, but we needed it to work at least for this weekend. So we've made some quick fixes. There's some epoxy and some JB Weld on there in places that you can't see, thankfully. And we came together and got that work. So a big thing of what we do on the team is we decide how long of a fix does it need to be, and then plan accordingly. How fast do we need to make it? How long does it need to last? How frantic are we, or can we actually redesign and come up with a long-term solution? So we have a lot of those moments. I know we've all had a lot of them in the past couple weeks specifically, but yeah.
Yeah, as you can see, this team definitely throws our members into the deep end a lot of the times, where we have to be able to think on our feet really quickly, make quick fixes that will last us just until we pass our next goal and are able to properly go ahead and redesign that system or that part, which is definitely something that's really cool that our team is able to do. We'll have to be able to do that throughout all of our testing sessions for the rest of the year, especially when we're out in the field at competition in the middle of the desert, in the middle of nowhere pretty much. We'll have to be able to think on our feet. There's no stores that we can go to in order to buy parts, buy tools. We have to be able to use what we have and come together and fix any problems that we run into. So that's definitely a really important skill, I think, that our team teaches all of our members, both while they're here at college, and then they kind of take that skill with them into the industry as they start working after graduation. Yeah, go ahead.
Yeah, because we're making it custom. Oh, the question was with Raman spectroscopy. You asked what the spot size was and if we were looking for just carbon peaks. Yep. So because it's custom, we're kind of just looking for whatever we can get. But throughout the year, we'll just test on various compounds and we'll just categorize them. So rather than identifying specific peaks, it's just more of an overlay. We look at one graph and compare it to another and see if it matches up or not. That's more of what we're doing. And as for the spot size, we're going to have a microscope objective on the very end that'll get it fairly small. I don't have the number off the top of my head. But does that answer your question? Awesome.
Yeah, go ahead. That's what was the biggest part we've broken, and what else? How much has it impacted our team? I don't know. MSIs maybe? Grant says he has a good one.
So last year, when we were working on the arm in the bay, we were messing around and switching out different types of forearms and putting stuff back on, and a couple interfaces got wacky there. As in, the number of bolts we had changed, their position slightly changed, so we made an adapter. So we put the adapter on one of the joints on the arm, and we put the whole forearm on, and then bolted together, and it's all going good and whatever, and then we try to lift 5 kilograms. And then the front of the arm fell off. There's been So that was interesting. We put it back on there. The bolts just didn't go in deep enough, so they just kind of left without much force at all. So definitely got that fixed. But at competition, we've had a year where half of the suspension, like one of the carbon tubes, I think, snapped during task. So we just kind of kept driving with that. It drives surprisingly well when the suspension is not intact. Yeah, those are the two biggest things that come to mind there. But we break some stuff. We broke the frame one year where the sides of the suspension were like tacoed up. It still drove surprisingly well. Like we were going over rocks at Fugitive Beach. Oh yeah.
So another thing, kind of fun. After competition last year, after we were done competing, there's an award ceremony where all the teams come together. And I can't remember which one it was, but we did both a tug of war and a race. And during one of those two events, one of our front wheels fell off. We were on the mountain. Oh yeah, we were going down the mountain, and one of our front wheels fell off. So we were driving with 5 wheels, and then we played tug of war, and we still managed to win with 5 out of 6 wheels on the Rover.
Also, on the way back from competition last year, we were packing up to leave, and we're on a tight deadline when we leave. We have people flying out for co-op opportunities, people that need to be at a very specific place at a very specific time. We try to leave, and there's a flat on the trailer. So after getting that fixed up, we hit the road, make it about 20 minutes down the road, middle of the desert, nowhere, Utah, and we get somebody radios over, because we're in a caravan type deal. Somebody radios over, the trailer is smoking. And our advisor was not too pleased about that. He said, this is not the time to play around. And they said, no, the trailer is smoking. We pulled over on the side of the highway in the middle of the desert, and one of the wheel bearings had exploded, and we got stranded. We had to leave the trailer with a few $1 million worth of equipment and everything we owned. We take the entire bay. In the middle of Utah, and had to have a repair shop come pick it up, and we had to split up and have people that had to fly out go and get to their flights. Then when they went to go pick the trailer back up, it made it from about Utah to Texas, and then it blew up again. So instead of just getting cooked in 100-degree heat, all of our electronics and everything we own got rained on for a few weeks. We brought home all of our electronic equipment, and it was swimming in water. So it had to sit on bench tops for a few days to get nice and dry. But
Awesome. That was a good question. Does anyone else have anything that they would like to ask? Go ahead.
Sure, yeah. So we do have a couple requirements with that, with it being like simulating you can't take an infinite amount of space or amount of weight to Mars. So before each task, each rover has to be in a configuration that weighs under 50 kilograms. And then all of the systems together have to weigh under 70, right? Is it 70 or 75? 70. So technically they never check that 70 requirement. So I would say it's loosely 70, but they are very strict. Part of that 10 minutes that we have to set up task is they have to weigh our rover and verify that it's under 50 kilograms, otherwise we can't compete. So that is a really big deal. We do a lot of what we're going to be doing the next couple months is cutting down weight on systems, because we've gotten everything together, but now we're going to make it as light as we can so we can add as many cool things as we can. So yeah, definitely a big consideration. Any other questions? Yes, go ahead. Go ahead, yeah. It is all-wheel drive. So there's 6 separate in these units on the front. There's individual motors. These are all propulsion units, so they all are individually wired to controllers inside the frame. So they do all drive at one time, and it does. The interesting thing about this rover, because it's not swerve drive, so the wheels can't turn on themselves. It is an interesting point turn. It can point turn, but it does make a nice little screeching sound along the ground if you're not on grass. But yes, so the steering is all-wheel drive, and then it can point turn and things like that. We control the rover with an Xbox controller or with a joystick, so it has pretty finite movements. We can bump it slightly or put it in full speed, and yeah, turn pretty sharply. Was there another question over here before that, or was there not? Maybe not. No, I don't think so. Online question? Yeah, go ahead.
they
like two completely separate rovers, and we have different systems. I guess, yeah, so we have, yeah. That is something we could do. That's the biggest conflict. There would be that 70 kilograms total weight requirement. Again, I don't know if they'd strictly check that, but if we did show up with two entire rovers, they'd probably be a little suspicious. But we could do that pretty easily, theoretically. We keep all our rovers from past years. Helios, last year's rover, is floating around here somewhere, was over by the mechanical table. But we keep them all in working order, largely for testing purposes and things like that. So we could have something like that. We do make changes. I know this year specifically, we changed our mounting system to the frame. So this is actually the only rover that our systems could interface with. But yeah, I would say space and weight is probably the only restraint that we'd have there. But it is like, that's feasible for our team the way we build something new every year. So possibility.
Is there another question over there? Yeah, go ahead. It's very answer on. Okay, the question was, what have you learned about being leaders and working as a team, right? Yeah, being in this position, I've definitely learned a lot throughout this entire year. I think the biggest one has probably been learning to work with all different types of people and all different disciplines of people. Not everyone thinks the same way you do. Not everyone is interested in the same types of things you are. Not everyone likes your ideas. Not everyone has the same ideas. And it can be hard to work in that type of environment where you have so many conflicting ideas and so many passionate members of your team who want their ideas to be heard and want to be able to explore all different types of things with our rover. So being able to kind of compromise in a lot of different areas with all the different members of our team, I think has been definitely the biggest one for me. Learning to give everyone a voice on this team, give everyone input into this team, because a lot of the times the best ideas on this team come from brand new members who have never touched any systems on the team and are brand new freshmen, and they're just thinking in a completely different way than we are. So yeah, I'd say that's probably the biggest one for me. Anyone to add?
Okay, similar to what she was saying, I attribute all of my basically technical and leadership experience to my experience on this team. I think one of the coolest things about this team, and I think is one of the reasons why a lot of us are leads, is because we do not care what experience you come in with. We will train you from the ground up and we'll support you in learning. Like, anyone can reach a high level position as an engineer. It really is, you get out of what this team, what you put into it. So I know that coming in my freshman year, a lot of people on this team did robotics in high school, came in with this technical experience, and I came in with none of it. I know I asked our CTO, Grant Bergstrom, on the day one of our first meeting what a gear ratio was. So we've come a long way since then, and being in a position like this is like mind-boggling to me, and I know also my parents, they're surprised. But yes, I have learned a ton, both like technically and then how to lead, and a whole different ballgame is learning that knowledge is teaching that knowledge. So I feel like I've had an entirely second different arc of learning my last 2 years on leadership, because I've had to know it well enough to be able to teach it to someone else, which is a huge thing. And a big, again, part of like working with others, like you said, is that nowhere else in your classes on campus will you get an opportunity to work with other disciplines like you do here. I would know nothing about electrical requirements, which is a big thing in industry, but it's not really what you get here. You work with other mechanicals, so I wouldn't consider electrical requirements the space they need for components, or similarly space for software components, or things that they need, viewing angles that they need for cameras, things like that we're not focused on, getting different perspectives, having to work and argue constructively with our peers to meet all of our requirements, not just mechanical ones. So I would say working with other disciplines and getting that experience that I wouldn't get anywhere else has been my biggest takeaway from the team as far as leadership and such goes. Anybody else? Yeah.
My biggest realization was coming to the understanding that it is infinitely harder to lift people up from above them, to remind yourself that you are still a human being, you are on the same plane as your members, and you are there as a resource and a mentor, that being a lead doesn't mean you have anything in particular above each of your members, but you are there to lift them up and make sure they get into the spotlight that they should be in.
Awesome. Probably do like one or two more questions before we go ahead and wrap it up. Anyone else have any other questions? Go ahead. Yes. Yes. So yes, is the SAR video a part of our University Rover Challenge score in the end, and have we been able to watch all of the other teams' videos? So the answer is yes. The The SAR video score is out of 100 points, and then each of the other 4 tasks actually at competition are also out of 100 points each, so total of 500 points. So this SAR video is worth 1/5 of our entire Rover score at the end of competition, which is a pretty big chunk of points. And yeah, basically the top 36 scoring teams that apply out of the 100 plus that usually apply each and every year get invited to actually go on site at the University Rover Challenge in Utah and compete their Rover in the 4 remaining tasks at competition. And yeah, we actually each year we usually have a watch party type thing going on. So this year we all met out at what's called Rove House, where we have a bunch of students who live in a house together that are on Rover, called Rove House. So we all met up there. We projected YouTube up on the side of the house. We got some lawn chairs out. We ate pizza, had drinks, and we all got to hang out and watch all of the other universities' SAR videos, see all the other cool, interesting things that other teams are doing, make fun of some of the other designs that other teams come up with, to be honest. Yeah, so it's a good time. We like to do that every year just to kind of see what our competition is and see what other teams are doing, especially the ones that have scored pretty high in past competition years that we have competed against. Oh, we should know in about mid to late March. They don't give us an exact date when they release the scores of our SAR video or if we are top 36. We have been top 36 since the beginning of our team and have consistently placed top 10 in the entire competition out of the 100 plus of teams that apply from around the entire globe each and every year for the past, I think, almost 12 years at this point, which I think is pretty cool. Question? Whatever. Okay, see this one? Good.
Do you think one of the reasons why you're so successful is you don't limit it to only grad students, you don't limit it to only seniors, but because you can jump in as a freshman, it gives you 4 years to compete and learn, and you're not just the first year that, but you've been doing it, learning the others.
Yeah, so that is actually one of my favorite things about our team is that you can jump in knowing next to nothing about anything, and you will get taught all of our e-board and our leads, our resources, as well as other members and our advisors, like Dr. Marmile right here. They've been an immense help to us, and I will say if we had limited this team in any way in terms of like just having graduate students or having people with experience, we would not be where we are today. I don't think we would have made it as far and sustained the team as long as we have. And as a geologist, I have learned so much about engineering things that I never thought I would, and maybe kind of didn't want to learn, but I did. And I can honestly say the opportunities that have opened up for me and for everyone else on our team have been amazing. And I don't think we would have been able to do it without being so open. All right, and we have one last question from our online audience, which is, what is something in particular that you want to highlight that maybe hasn't been highlighted today? So, do any of you guys want to answer that?
So for science specifically, and I'm sure all of the other sub-teams, you see all of the projects sitting out on the tables, but you can't really see all of the work that has gone into them. All of the intense work, the late nights, the times where you've wanted to just bang your head on the desk because you couldn't find any resources on what you're researching. But I want to highlight all of the work that has been done by every single one of my members over there. They will all try to downplay the work they've put in, but they have done an absolutely phenomenal job in putting a science system together that I could not be more proud of. So, good job, everybody over there.
All right, thank you for all of the good questions. I'm excited we got so many questions this year. We love answering those. So yeah, we'll go ahead and wrap it up there. Before we kind of break down and start taking group photos and individual photos with the Rover, I just want to go ahead and thank all of you parents and family and friends out here for your support for each and every one of these students that we have here with us, working with us today. I know they spent a lot of time on this team and put in a lot of hard work, and it can get stressful at times. So I want to thank you all for supporting them throughout their journey on this team. I want to thank the Design Center for obviously hosting us in this awesome facility that enables us to be able to create so much of our own things, have so much professional equipment to work with, and we're just able to do so much with the situation that we're in. And then finally, I want to thank our advisors, Dr. Mormile, who's standing over there, Dr. Ramsey, and Dr. Grubbs. They have all been advisors that our team and our e-board can go to for advice and anything that we need help with, and they have definitely been so helpful for us throughout the entire year as we navigate our leadership positions and try to run this team each and every year. So thank you all for showing up today. I hope you all had a good time and was able to learn a lot about what your students are all working on. And from here, we will kind of break off and try to get some pictures taken. Before I go, quick plug, if you want any more information about how to check us out, how to support the team, you can go to marsrover.mst.edu. It'll take us to our design team website, so you can learn about our team history, ways to get involved, see more about everything that our team does. So yeah, that being said, again, thank you all for coming out. We'll go ahead and break off into trying to get some group pictures in this room. That might be kind of difficult, but I'm thinking we have all of our members will do one big team picture at first up front, and then try to have everyone else kind of scoot back that way. That way we can fit everyone up here and get a good picture. So thank you all for coming out.